Hello everyone, welcome. This is the pre-calculus course for summer 2, 2021. And we shall start with a review from algebra, some very basic notions from algebra. The review will be conducted in two parts, part 1 and part 2. In part 1, we shall review some basic properties of real numbers, absolute values, inequalities, and interval notation. And in part 2, we'll talk about some very basic algebraic structures, factoring methods, and so on. So let us start with part 1. I'm going to share the screen, and as I speak, I will write on my notepad, and you will have this as a PDF posted to Blackboard. Okay. Give me a moment. See. Moment. Okay. So, as I said before, I'll say things and I'll write them. Of course, I'll supply examples as well. So this is review, part 1. And we will talk about some basic property of real numbers, absolute value, inequalities, and interval notation. Okay. So let's start with real numbers. What do we mean by real numbers? So I'm just put my glasses on. All right, so what do we mean by real numbers? Are they divided into some categories? And yes, they are, and we have seen those categories before. So the set of numbers that we most comfortably with, or the set of numbers that we best know, is the set of natural numbers. Natural numbers are otherwise known as counting numbers. So what are those? Those are the numbers that we use to count. Hence the name natural numbers, 1, 2, 3, 4, and so on. So notation for this is this capital N with this double line here. So this is the set of all natural or counting numbers. Okay. Or otherwise, the set of whole numbers, but the positive ones. So the set of natural numbers consists of numbers like 1, 2, 3, 4, 5, and so on. Okay, these three little dots indicate that this is a set that goes to infinity. You can never stop counting those. All right, so the next grouping of numbers would be the so-called set of integers. Integers are otherwise known as whole numbers. They are positive, negative, and this set also includes number 0. So notation for the set of integers is this capital Z. So this is set of all integers. Integers is another word for whole numbers. Okay. Okay. So positive, negative, and zero. And zero. All right. So the set of all integers, it's a set that extends to infinity on both directions. There is no starting point from one end to the other. So for the moment, you may think of it like this. I mean, -4, -3. There is no specific reason why I started at -4. You could start at -11, at -100. It doesn't really matter. Those, again, these three dots here indicate that I have infinitely many numbers, negative whole numbers before -4. -4, -3, -2, -1, 0, 1, 2, 3, 4, and so on. Okay. All right. So another grouping of numbers is the set of all rational numbers. So what are those? So this is the set of all rational numbers. Okay. So what are those? I'm just going to write a loose definition of what do we mean by a rational number, but we have seen rational numbers before. Rational numbers are all numbers that can be written as the ratio of two integers, as a fraction. But when I say as a fraction, I don't mean a decimal number over some other decimal number, or pi over some number. I mean a whole number over some other whole number, with the understanding that the number on the denominator on the bottom is not zero. So here's a loose definition of what we mean by rational numbers. So rational numbers are all numbers that can be written as the ratio of two integers. Such that the denominator cannot be zero, where the denominator cannot be zero. Okay. That means all numbers of the form a over b, where a and b are any two integers and b is not zero, are any two integers and b is not zero, and b is not zero. So here are some examples. -1 over 5 is a rational number. 32 over 6 is another rational number. Number 3 is a rational number. Why? Because number 3 can be written as the ratio of two integers, namely as 3 over 1. 3 divided by 1 is 3. So number 3 is another way of being written as 3 over 1, meaning as the ratio of two integers. 0 over 18. That's just another way of writing the number 0. So 0 is also a rational number. 1/3 is also another rational number, and so on. Keep in mind, for example, that number 1 over 3 or the ratio 1 over 3 could also be written as a decimal. What sort of decimal? The kind of decimal whose decimal expansion never ends and it has a repeating pattern. The repeating pattern here is just the threes. So if you divide 1 by 3, uh, that is another way of writing 0.333 with 3's never actually ending. So this sort of special decimal also represents a rational number. So uh, in that context, we can also say that decimal numbers whose decimal expansion, by decimal expansion we mean what comes after the decimal point, whose decimal expansion either ends or it has a never-ending repeating pattern, a never-ending repeating pattern is also a rational number. Is also a rational number. Okay, so here's an example. As I said before, 1 over 3 is another way of writing this other decimal number. So they both represent the same thing. So this decimal number and this fraction represent the same rational number. So rational numbers could be coming in two flavors. They may be looking like fractions or like decimal numbers. Keep in mind, if they look like decimal numbers, they have to have these two properties in them. The decimal expansion either ends or it has a never-ending repeating pattern. So if it's a decimal, it should fulfill one of those two conditions. Or 0.25, for example, it's the same as writing 25 over 100. 25 over 100 is a fraction, is the ratio of two integers, whereas 0.25 is a decimal number, but the decimal expansion ends at 5. It doesn't have a never-ending repeating pattern. So it fulfills one of these conditions. Or the number, for example, 14.032 with a bar on the top. The bar on the top means that 32 is the block of digits that keeps repeating to infinity. So that's another way of writing 14.0323232 with the three twos never ending. Just to save space, we put a bar on the top of 32 to indicate that 32 is the block that repeats itself endlessly. Okay, numbers 0.1, 2, 3, 5, 6, and so on. Certainly, it has a decimal expansion that never ends, but it doesn't have a repeating pattern. As such, is not an example of a rational number. It's a decimal number that is not rational. So, is a decimal number that is not rational. Because it has a never-ending decimal expansion, but there is no repeating pattern there. If it has a never-ending expansion, there must be a pattern that repeats to infinity, just like this number here. And that's not the case with this number. Okay, so what is the set of irrational numbers? So irrational numbers, notation for irrational numbers is this capital I, and that indicates the set of all irrational numbers. Set of all irrational numbers. Set of all irrational numbers. So what are irrational numbers? Irrational numbers are all numbers that are not rational. Numbers that are not positive integers, negative integers, and so on. So everything that's not a rational number is called an irrational number. So again, here's a loose definition of what we mean by an irrational number. Irrational numbers are all numbers that cannot be written as the ratio of two integers. That cannot be written as the ratio of two integers. Okay? Or a number whose decimal expansion never ends and it does not have a repeating pattern. And it does not have a repeating pattern. Okay. So both for a decimal number to represent an irrational number, both of these conditions must be fulfilled. That's why I'm indicating this and here, because this should be true and this should be true for a decimal number to be called irrational number. So some examples of irrational numbers that we all know is the famous number pi. So examples. You all know that pi is approximately, is not 3.14, but it's approximately 3.14. That indicates that it has a decimal expansion. Not that it indicates, but it's a known fact that it has a decimal expansion that it never ends, and it does not have a repeating pattern. Square root of 2 is another example. It's about 1.414 and so on. But again, the decimal expansion does not have a repeating pattern, it never ends. Those three dots always indicate that the numbers continue. So the set of all rational numbers together with a set of irrational numbers form the so-called the set of all real numbers. So this notation means union of two sets, two or more sets. So this means the set of rational numbers together with the set of irrational numbers make the so-called the set of real numbers. So we have seen that real numbers can be represented graphically, how they are represented in some imaginary straight line that extends to infinity on both directions. And the imaginary middle of this line is the position that represents number 0. To the right of 0, we write all positive real numbers. So 1, 2, 3, 4, and so on. To the left of 0, we write the negative real numbers, -1, -2, -3, -4, and so on. So in between any two integers, there are infinitely many real numbers, rational and irrational. For example, somewhere between 1 and 2 lies, let's say, the square root of 2. Somewhere here, you have the square root of 2. Somewhere here, you have pi. Somewhere here, let's say, you have 1/2, and so on. So something that is very important, real numbers are ordered. What does that mean? Let me just write this first. Real numbers are ordered. That means given any two real numbers, one is less than the other, or they are equal to one another. So if A and B, A and B are any two real numbers, then the following is the possibilities of A being somehow ordered are 3. Then we say that uh, either A is less than B if B minus A is greater than 0. B minus A is greater than 0. The same goes for greater than, less than, greater than or equal, less than or equal. Here's an example. A less than B geometrically means that on the real line, A is positioned to the left of B. Okay. So geometrically, means that A lies to the left of B on the real line. For example, to say that x is less than or equal to 2, or to say that x is the set of numbers that are less than or equal to 2, how do you represent that? If this is 0, this is 1, this is 2. This means all numbers that are less than or equal to 2. So this would mean that we're talking about all numbers that lie to the left of 2. So all numbers that lie to the left of 2, including number 2, are the numbers that are represented with this expression. Okay, what about all numbers that are greater than or equal to -3 but less than 2? Geometrically speaking, how do you represent them in the real line? Okay, again, let's point out where -3 and 2 are. So this is 0, this is 1, this is 2, -1, -2, -3. So we're talking about all numbers that are greater than or equal to -3, which means that they all lie to the right of -3, -3 being included, and all numbers that lie to the left of 2. So all numbers that are greater than or equal to -3 means all numbers that are to the right of -3, -3 included, and at the same time to the left of 2, but 2 is not included. This means strictly less than 2, not less than or equal to 2. So we're talking about all these numbers that are between -3 and 2. Okay, so more formally, let me remind you of the intervals. What do we mean by intervals? Okay. Here, A and B are any two real numbers. Okay, so A, B, this is the closed interval A, B. These square brackets indicate that we're dealing with a closed interval. What does a closed interval mean? It means that we're talking about all numbers that are greater than or equal to A and less than or equal to B. So this means all numbers that are greater than or equal to A but less than or equal to B. In the real line, if this is A and this is B, then we're talking about all numbers that lie on that part of the real line. Okay, A and B is included. Okay, so what does the open interval A, B means? This means the set of all real numbers between A and B, or the set of all real numbers that are strictly greater than A and strictly less than B. So this means, you should have seen this before, all numbers that are strictly greater than A but less than B. So in the real line, if this is A and this is B, we mean all real numbers between A and B, but A and B are not included. So the open brackets, I mean the round brackets indicate that A and B are not part of this bunch of numbers. Okay, so half open or half closed interval AB means all real numbers that are greater than or equal to A, but strictly less than B. So it means all numbers X that are greater than or equal to A, but less than B. Again, graphically, This means the following. This is A, this is B. So A is part of it, B is not part of it, and everything in between is included. Okay. This is called a half open or half closed interval. Either way you say it, you are not wrong. Similarly, we have the half open or half closed interval AB, where B is part of it, but A is not. So this means all real numbers that are strictly greater than A, but less than or equal to B. Graphically speaking, we have this, A, B. So A is not part of it, B it is, and of course, everything in between. So half open or closed interval A positive infinity means that we're talking about all numbers that are not strictly, that are greater than or equal to A. And everything that's greater than or equal to A. So this means all x that are greater than or equal to A. In the real line, we're talking about all numbers that are to the right of A, including A, and they go to infinity. Minus infinity A included, means all numbers that are less than or equal to A. Okay. But A is included. So we're talking about all numbers, including A, that are to the left of A. Similarly, we can talk about open interval A plus infinity or open interval minus infinity. So A positive infinity means all x that are strictly greater than A in the real line if this is A is not included. So everything that's to the right of A, but A is not included. Minus infinity A, that's the open interval minus infinity A, that is, means all x that are strictly less than A, graphically speaking, means all numbers that are to the left of A, but A is not included. And the open interval minus infinity plus infinity means all real numbers. Okay, so all of these are things that hopefully you have seen before. Let us talk a little bit about the absolute value, the notion of absolute value. Okay. So what do we mean by the absolute value of some number A? Here is a definition. So the absolute value of real number A real number A, or let's call it a real number B, indicates the distance of this number b from the origin. Before I write the definition, you probably know that no matter what, the end result of the absolute value of a number is always positive. And that corresponds with this definition of a distance. The distance as a notion can never be a negative quantity. Whenever you talk of a distance, it always is a positive quantity. So in the real line, the absolute value indicates a distance. So no matter how you define it, the end result of that absolute value or the end result of, according to that definition, should be always a positive quantity or a positive number. So number b is the distance, between the number of b from 0 on the real line. So definition of, well, this is the notation for the absolute value. And the absolute value of b is defined to be just the number b itself. If the number b inside those absolute value signs is positive, and is negative if the number is negative. For example, the absolute value of 5 is equal to 5 because the number that's inside the absolute value signs is just positive. The absolute value of -7 is equal to be, according to the definition, minus that number if the number is negative. So what's inside the absolute value is -7. -7 is a negative number. So according to this definition, the absolute value of -7 should be minus number 7, minus number 7, and we know that minus a number is just that number. That's why the end result of the absolute value, according to the definition, is always something that is positive. So what are some of the properties of the absolute value? Okay, so properties. So the absolute value, as I said before, of some number is always a quantity that is positive or zero, because we can always talk about the absolute value of 0, which is 0. So the absolute value of a negative number is the same as the absolute value of that number, but the positive part of it. The product of the absolute value of two numbers, so the absolute value of some number A times some number B, is equal to the absolute value of the number A times the absolute value of number B. Similarly, the absolute value of the ratio of two numbers is equal to the ratio of their absolute values, provided that B is not 0, of course. Okay, so we use the absolute, since by definition it is the distance of a number from 0 on the real line. We use the absolute value oftentimes to define the distance between any 2 points on the real line. How? So let me just give the definition first. So absolute value is used to define the distance between any 2 points on the real line. Any 2 points on the real line. Okay, so What do I mean by that? Here's the definition. D stands for distance. We're saying that the distance between point A to point B. So this does not now indicate an open interval because I have the letter D in front of it. So by that, I mean the distance between A and B. Okay, the context of this set of brackets here is completely different from what we mean by an interval, as I explained before. So the distance between A and B is defined to be as the absolute value of B minus A. But of course, this absolute value, according to the previous properties, is the same as the absolute value of A minus B. For example, the distance between minus 2, the number minus 2, and the number 8 on the real line, according to this definition, is the absolute value of 8 minus 2 minus minus 2. And that is the same as the absolute value of 10, which is 10, or uh, is equal to minus 2 minus 8, which is the absolute value of minus 10, and the absolute value of minus 10, according to the definition of absolute value, is still 10. So no matter how you write that difference between these two numbers, either b minus a or a minus b, it means that you will always get the same positive number, the same result, and that will be the so-called distance between these two numbers, just as in this example. Whether you write it a minus minus 2 or minus 2 minus 8, the absolute value of that end result is always 10. So the distance between minus 2 and 8 in the real line is exactly 10 units. So they are 10 units away from one another. Okay, so let us talk now a little bit about, since we talked about intervals, intervals naturally will lead to the notion of inequalities in one variable. So what are some examples of inequalities? Inequalities are much like equalities, except that they don't have just an equal sign, but between two expressions have either less than or equal, greater than or equal. Inequalities in one variable. Um, what are some examples of inequalities in one variable? 5x minus 7, for example, less than 3x plus 9. So that's an example of an inequality in one variable, namely variable x in this case. Here's another example, minus 3 less than or equal to 6x minus 1 less than 3. Here's a double inequality, again, in one variable. So what are some of the properties of inequalities? I shall list them all and give you some examples as well. So properties of inequalities. Okay, so the first one is the so-called transitive property. What does that mean? Transitive property means the following. If some number A is less than some number B, and that same number B is less than some other number C, then it means that the number A, then number A must be less than number C. Okay. Two, the additive property. What is that? If number A is less than number B, and number C is less than some other number D, then A plus C is less than B plus D. A plus C is less than B plus D. Addition of a constant. What is that? If A is less than B, then the end result or the inequality will not change if you add the same constant at the same time to both sides. So if A is less than B, then A plus C is also less than B plus C. So all I did is added the constant plus C to both sides of this inequality and nothing changes, meaning the value of the inequality does not change. Okay, multiplication by a constant, similarly. By a constant. If A is less than B, we need to consider two cases here. So for C being a positive constant, if A is less than B, then the same remains if you multiply both sides of this inequality by the same positive constant. Then A times C is also less than B times C. So if I multiply both sides of an inequality by the same positive constant, then nothing changes. The value of inequality is the same. However, if this constant is a negative number, so if C is negative constant, then if A is less than B, when you multiply both sides of this inequality by a negative constant, the direction of the inequality will reverse. So then A times C is greater than B times C. It's not the same as the previous one. The inequality, the direction of inequality when you multiply by a positive number does not change. But if you multiply by a negative number, the direction of the inequality reverses, changes. Here are some examples. Here are some examples. So let's say that you have this inequality that you want to solve. The first one that I just put there, 3x plus 9. How do you solve this inequality using the properties that I just listed? Okay, so much like you behave with solving an equation, you'll do more or less the same things here. If you have an equation, typically we move all the terms that contain the variable on one side, isolate them on one side, and everything else on the other side. You achieve this by adding or subtracting the same quantity from both sides of the equation, in this case, from both sides of the inequality. So let's say that you want to put things that contain x on one side of inequality. Let's say you want to put them on the left-hand side. So to do this, you will add negative 3x to both sides of this inequality. So I added negative 3x to both sides. I am allowed to do this by property number 2. Property number 2, it says, property number 3. If you have an inequality, then it's okay to add the same thing to both sides of this inequality. So I have an inequality and I'm adding to both sides of this inequality minus 3x. This is by uh, property number 3. I am allowed to do this. So 5x minus 3x is 2x, minus 7 stays where it is. 3x minus 3x is 0. 0 plus 9 is 9. Okay, so now you want to get the 2x by itself. To get the 2x by itself, you need that minus 7 to be moving on the right-hand side. Again, you achieve this by adding negative 7, by adding, I'm sorry, 7 to both sides. So here you are going to add 7 to both sides. Again, this is by property number 3. So plus 7 minus 7 is 0. So you're left with 2x on the left-hand side. Right-hand side, you are left with 9 plus 7, and that is 16. Okay, we're almost there. Now I need the x by itself. To do that, I need to multiply both sides of this. I need to divide both sides of this inequality by the coefficient in front of x, which is 2. So that's the same as multiplying both sides of this inequality by number 1 over 2, which is the same as the property number 4, multiplication um, by a positive constant. 1 over 2 is a positive constant. So I repeat, dividing by 2 is the same as multiplying by 1/2. So this implies that we're dividing by 2 or multiplying by half. Actually, let me just write this down. So 2, I'm multiplying both sides by 2x, by 1 over 2. So 2 and 2 cancel here. You are left with x. 16 divided by 2 is less than 8. So that's the solution, almost there. You need to write that as an interval. So how do you write x less than 8 as an interval? So solution is all numbers that are strictly less than 8. As an interval, you write that as minus infinity 8, but 8 is not included. Okay. If you go back here, I'm sorry, I'm going back a couple of steps. Minus infinity a means all numbers that are to the left of a. So x being less than 8 means all numbers to the left of 8, or you write a solution as this open interval minus infinity 8. Okay, so much for this first part of review. We shall move to the next part of the review that deals a little bit with the rules of algebra. I'll see you in a bit.